Hello and welcome to this tutorial of quantum physics in the Australian bush, and in this episode, this tutorial, I'll cover a basic introduction to the first quantum particle, the electron. It's a fairly central one. It's part of atoms, molecules and crystals, but we're going to look at a few basic things about it, some basic properties, and then in future episodes we'll go through the grinding history of how we've discovered it. So fundamentally, electrons were made in the Big Bang. Now, the Big Bang happened 13.7 billion years ago, and remarkably we can point our telescopes up in the sky and see the actual moment of the Big Bang. So it's all around us. It's a big blinding flash of light. Of course, the light over time has stretched, so stretched from the visible infrared. It's now sitting at a mobile phone frequency out in space. But in that time, the Earth is very small. Sorry, not the Earth, the universe is very small, and if you can imagine, much smaller than this leaf here. All that universe and all that light going in, the light beams came across, pushed into each other, and knotted up the space. And doing a particular way, the space couldn't unknot, the light was trapped, and you made an electron. Now, I'm saying this as a way of trying to visualize how the electron was made, because nowadays we know if you get an electron and an anti-electron, they come together, the space are knots, the mass disappears, or the stretchiness of space disappears, and the two beautiful beams go out. So just reversing the camera if you'd like, or playing in reverse, two light beams come in, and we make an electron and a positron, an anti-electron. Now, that may not help you, but there are four basic types of bottom rung of electrons. There's several types of electrons, but bottom rung is there's positrons, normal electrons, spin up, spin down. And let me try and describe it. So the term of spin, that is a feeling of, even though it's got no spatial dimensions, it's actually spinning this way or spinning that way. And you can sort of imagine it from its creation, but it's beyond really our understanding. So an electron has a mass, and mass is a very vague sort of term. The word mass comes from Greek for dough, so they have an idea of the substance of it. But for us, nowadays, there's several ways of looking at it: how hard it is to throw, how you push it, how far it goes, and sort of the weight that it feels. If you have a mass in a gravitational field, that creates some weight. So an electron has a very tiny mass, and its mass is 1,837 times smaller than a proton. How much does a proton weigh? In science, we made it rather easy for ourselves, because we've decided that a proton weighs the mass of 1 unit. Makes it rather easy. When I say unit, the word unit itself is now a unit. So we've got kilograms for, say, butter and water, or things like that. But for atomic particles, we've used the idea of U. So I've got these two coins here, because if you added up all the electrons in your body, and you could actually hold it in your hand, it would be the weight of 2 coins. The mass of that would be the mass of the electron, and the rest would be the mass of your body. The size of electron, well, that's a contentious issue. A lot of people believe that it's really, really small, much smaller than a neutron or proton, because it's so light. But this is a bit of spoiler alert. In quantum physics, the smaller or less massive it is, the larger its wave function. So that's going to be an issue that we have to deal with at some stage. And of course, let's not forget that electron itself has a charge. Again, to make things easy, we've said that the charge on an electron is equal to the charge of 1 electron, and we write that as minus E, or it's a negative charge, and it's the value of E, charge of an electron. So just in summary again, the electron, there's lots of electrons about. Electrons are very low mass compared to that of a proton. They have a charge of 1e, they've got a very, very small magnetic field, due to this spin, and this is a charge that spin together. And just to give you an idea, the magnetic field is 10 to the 44 times smaller than that of the Earth. So if you have an electron here and the Earth here, the strength of this magnetic dipole is 100 million times smaller than the Earth. And finally, it's got size, and we'll have to deal with that later in a different issue, a different episode.